You think energy is continuous. Most people do. It feels obvious. You turn up the volume on your phone. It gets louder, smoothly, gradually. You dim a light, it fades. You push something harder. It accelerates more. Energy seems to flow like water, infinitely divisible, smooth. That's not what reality does. And the strange part, the person who discovered this didn't want to believe it either. This isn't about quantum mechanics as a theory. It's about what Max Planck found when he wasn't looking for it. Something so fundamentally wrong with the universe that it forces you to reconsider what continuous even means, what smooth means, what it means for something to happen at all. Most explanations will tell you Planck discovered that energy comes in packets. That's true, but that's just repeating words. That's a label. It doesn't tell you why that changes everything. It doesn't tell you what it means for reality to have that property baked into it at the lowest possible level with no deeper reason underneath. Let's start somewhere simple. Imagine you're holding a metal rod. One end is in a fire, the other end is in your hand. Heat flows from the fire to your hand. You feel it. The rod gets warmer. Energy is moving. Now ask yourself, what is that energy doing while it moves? You might say it's spreading, vibrating through the atoms, transferring. Fine, but is it flowing smoothly, like water through a pipe? Or is something else happening? For most of human history, we assume smooth, continuous. Energy was treated like a fluid or a wave or a field, something that could take any value, transition through every possible state, divide forever. That assumption was built into the math. It was built into the physics. And for a long time it worked, until it didn't. By the late 1800s, physicists had a problem. A very specific, very annoying problem. It involved something simple. A hot object glowing. Heat anything up, a piece of metal, a coal, the filament in a light bulb, and it glows. The hotter it gets, the brighter it glows, and the color changes. Red, orange, white, blue. This is called black body radiation. It's one of the most ordinary things in the universe. Physicists tried to calculate how much light a hot object should emit at different wavelengths. They used the best theories they had: classical physics, thermodynamics, the wave theory of light, everything that had worked beautifully for decades. The math said, as you go to shorter wavelengths, ultraviolet, X-rays, the amount of energy emitted should go to infinity, not just a lot, infinity. That's called the ultraviolet catastrophe. And it wasn't a rounding error. It was the theory eating itself. It meant that every warm object in the universe, your hand, a cup of tea, a rock, should be emitting infinite energy. Obviously that doesn't happen. So something was deeply, fundamentally wrong. This is where Max Planck enters. Not as a revolutionary, not as someone trying to overturn the laws of physics. He was a thermodynamicist, a conservative one. He wanted to fix the equation, make it match the data, move on. In 1900, Planck found a formula that worked. It fit the experimental curve perfectly. But to make the formula work, he had to add something strange. He had to assume that the energy emitted by the hot object wasn't continuous. It came in chunks, discrete packets, little units. He called them quanta. The size of each packet was proportional to the frequency of the light, tied together by a tiny constant now called Planck's constant. This wasn't a deep physical insight for him at first. It was a mathematical trick, a way to make the integral converge. He thought maybe eventually someone would find the real explanation and this discrete business would go away. It did not go away. What Planck had stumbled into wasn't just a fix for blackbody radiation. It was a property of reality itself. Energy doesn't flow. It jumps. Let that sit for a second. When an atom emits light, it doesn't gradually lose energy. It loses a specific amount all at once. When an electron moves between orbits in an atom, it doesn't slide smoothly from one level to another. It disappears from one and appears in another. No in-between, no transition. This isn't because we can't measure the in-between. It's because there is no in-between. The universe at its most fundamental level is not smooth. It is granular. You can't have half a quantum of energy, the same way you can't have half a pixel on a screen that's already at its smallest resolution. Reality has a resolution, and Planck's constant defines it. Now, here's where it gets strange. Planck's constant is incredibly small. In everyday units, it's about 6.63 times 10 to the negative 34 joule seconds. That's why you don't notice this in daily life. The steps are so tiny that everything looks smooth, the same way a digital photo looks continuous even though it's made of pixels. But the smallness doesn't make it less real. It makes it more unsettling, because it means the discreteness is always there. You just can't see it until you look closely enough. This discreteness isn't just about energy. It's linked to something deeper. Planck's constant appears everywhere in quantum mechanics. It connects energy and frequency. It connects position and momentum. It defines the scale at which the universe stops behaving classically and starts behaving quantum mechanically. But more than that, it enforces a boundary. There is a limit to how much information you can extract from reality, a limit to how precisely you can know certain pairs of properties at the same time, a limit to how finely you can divide action the products of energy and time. This isn't a limit of measurement, it's a limit of existence. You cannot have a process in the universe that involves an action smaller than Planck's constant. If you try to build a system with less action than that, the system stops making sense. Position becomes undefined, time becomes undefined, cause and effect blur. This is not a technological problem. You can't build a better instrument to get around it. The universe itself doesn't provide information. Because the information doesn't exist, the universe has the smallest meaningful unit of action. Below that, the question what happens has no answer. Not because we don't know. Because the question is malformed. It's like asking what's north of the North Pole. Planck didn't set out to discover this. He was solving a radiation curve. But what he found was that reality has seams, joints, edges, places where the smooth story we tell ourselves breaks down, and something more fundamental takes over. That constant, that absurdly tiny number, is the signature of a universe that is put together differently than we thought. Here's the part that no one really explains. You might think, okay, energy is quantized, fine, but why? What's underneath that? What mechanism makes energy come in packets? There isn't one. This is the bottom. There is no deeper why. Planck's constant isn't derived from something more fundamental. It's a basic feature of the universe. You can't explain it in terms of something else, because there is nothing else beneath it. It's written into the fabric of reality the same way the speed of light is, or the existence of space itself, and that should bother you, not because it's wrong, because it's true. We are used to explanations that go deeper. You ask why water boils, you get atoms. You ask why atoms bond, you get electrons. You ask why electrons behave that way, you get quantum mechanics. But when you ask why quantum mechanics has this discrete structure, the answer is it just does. Planck's constant is an axiom of existence. It doesn't emerge from something simpler. It's one of the rules the universe runs on, and there is no rule beneath it. This is not ignorance. This is the shape of reality. Now, you might wonder if this is so fundamental, where do we see it? How do we know this isn't just philosophy? We see it everywhere. Once you know where to look, every time a photon is emitted or absorbed, every pixel on your screen, every signal from a distant star, every chemical reaction in your body, it obeys this rule. The energy of that photon is Planck's constant, times its frequency, always, no exceptions. When scientists built the first lasers, they were manipulating discrete quantum states. When they developed transistors and semiconductors, they were working with electrons, jumping between quantized energy levels. When they measured the cosmic microwave background radiation light from the early universe, they saw the signature of flat body radiation, the very thing Planck was trying to explain. The technology you're using to watch this right now only works because engineers understood that energy is quantized, that electrons don't flow smoothly, that light comes in packets, that Planck's constant is real. This isn't theoretical. It's not abstract. It's verified billions of times a day in labs and devices all over the world. But there's something even stranger. Planck's constant also sets the boundary for another kind of limit. It appears in the Heisenberg uncertainty principle, which says you cannot simultaneously know the exact position and exact momentum of a particle. The product of the uncertainties is always at least on the order of Planck's constant. Why? Because reality doesn't store that information. A particle doesn't have a precise position and a precise momentum at the same time in the way we think of objects having properties. The universe doesn't work like that. And Planck's constant is the number that tells you how much ambiguity is baked in. This ties back to the same thing. The universe has a resolution, a graininess, a smallest scale of action. And once you hit that scale, the classical picture smooth, deterministic continuous falls apart. You can't zoom in forever. There is a flaw. Planck himself didn't fully accept this. Even after his discovery, he spent years trying to find a way to restore continuity, to make the quantization go away. He couldn't. No one could, because it's not a mistake. It's the truth. And here's the strangest part of all. The size of Planck's constant, tiny as it is, determines the character of the quantum world. If it were larger, quantum effects would dominate everyday life. Objects would tunnel through walls. You'd see interference patterns in thrown baseballs. Uncertainty would be obvious. If it were smaller, the quantum world would be even more hidden. You'd need even more sensitive experiments to detect it. The universe would look more classical, more Newtonian, more like the smooth, deterministic machine people once thought it was. But it has the value it has. And that value makes our universe quantum, but only barely. Just enough that atoms are stable. Just enough that chemistry works. Just enough that life can exist in a world that's mostly predictable, but fundamentally strange underneath. Planck's constant isn't just a number. It's the knob that tunes how quantum the universe is. And you don't know why it has the value it does. You can measure it, you can use it, you can build technology around it, but you can't explain it. It's given. This is what Planck discovered. Not that energy comes in chunks, that's the fact, but that the universe, at the deepest level we can reach, is not continuous. That there is a smallest unit of action. That reality is quantized. And that below that quantization there is no further structure, no deeper explanation, no hidden guess, just a constant, a number, a boundary. Think about what this means for a moment. Before Planck, the assumption was that you could always go smaller, you could always divide further. There was no bottom to the scales of nature. Space was infinitely divisible, time was infinitely divisible. Energy could take any value, no matter how small. This wasn't just a practical assumption, it was a philosophical one. It shaped how people thought about the universe. Reality was a continuum, smooth, elegant, deterministic in principle, even if chaotic in practice. Planck's discovery shattered that. It said, no, there is a bottom, there is the smallest step, there is a point where further division becomes meaningless. Not because we lack the tools, but because the universe itself doesn't provide the space for it. This has profound implications. It means the universe is fundamentally different at small scales than it appears at large scales. The smoothness you see is emergent, it's statistical, it's the result of countless discrete events blurring together. It means that continuity, the thing we take for granted, the thing that makes calculus work, the thing that makes motion and change comprehensible, is an approximation. A very good approximation at human scales, but an approximation nonetheless. At the foundation, reality is digital, not analog, and that's deeply strange. Because it means the universe has more in common with a computer simulation than with a flowing organic picture, we inherited from classical physics. Not that the universe is a simulation, there's no evidence for that, but that it has a discrete structure. It operates in steps. It has a fundamental resolution. This also connects to something else that most people don't think about. When you watch a film, you're seeing 24 frames per second. Each frame is a static image, but your brain blurs them together into smooth motion. The motion isn't real, it's constructed by your perception. The universe does something similar. The motion you see, the flow of energy, the passage of time it is, are made of discrete quantum events happening so rapidly and so small that they appear continuous. But underneath it's step, 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 step. Jump, 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 jump. Reality flickers. You don't notice it because the flicker is happening at the scale of Planck's constant. But it's there. And once you know that, you start to see the universe differently. You start to realize that the smoothness is the illusion. The discreteness is the truth. Now, let's go deeper into what this actually means for causality. In classical physics, cause and effect are clear. You push a ball, it rolls. You heap water, it boils. Every effect has a cause, and every cause produces an effect. The chain is unbroken. The universe is deterministic. But Planck's discovery undermines that picture in a subtle way. If energy is quantized, then processes can't happen gradually. An atom can't slowly release energy. It has to release a quantum all at once. An electron can't drift between orbits. It has to jump. This introduces a kind of discontinuity into the causal chain. There are moments where something is in one state and then, without passing through intermediate states, it's in another state. What happened in between? Nothing. There is no in between. This isn't a gap in the process. It's the absence of a process. The transition is instantaneous, at least in the sense that there's no time during which the system is in a transitional state. This is where quantum mechanics gets strange, and it all starts with Planck's realization that energy doesn't flow, it jumps. That discreteness propagates through the entire structure of quantum theory. It's why quantum mechanics is probabilistic. It's why you can't predict exactly when an atom will emit a photon. You can only calculate the probability. It's why the universe at its core seems to involve randomness. Not randomness because we don't know. Randomness because that's how it is. The universe makes decisions, in a sense. And those decisions happen at the boundaries defined by Planck's constant. This is unsettling. It should be. It violates our intuition about how things work. But it's real. And it's been confirmed over and over in experiment after experiment for more than a century. There's another implication that almost never gets discussed. Planck's constant defines the boundary between the quantum world and the classical world. It sets the scale at which quantum effects become noticeable. Where large objects base was scarce, planets' quantum effects are negligible. The steps are so small compared to the object's size and energy that everything looks smooth. Classical physics works. But for small objects, atoms, electrons, photons, steps are comparable to the system itself. Quantum effects dominate. You can't ignore them. This means the universe has two regimes, two different sets of rules, or rather, one set of rules, quantum mechanics, that behaves differently depending on the scale, and Planck's constant is the dividing line. It's the number that tells you when the universe stops acting classical and starts acting quantum. But here's the key. The quantum behavior is the fundamental behavior. The classical behavior is what you get when you average over many quantum events. Classical physics is not more real. It's less real. It's the blurred version. The quantum level is the true level, and Planck's constant is the signature of that truth. It marks the scale at which the universe reveals itself as it actually is, not as it appears to be. Now let's talk about what happened after Planck. Because even though Planck made this discovery in 1900, he didn't really believe it. He thought it was a temporary fix, a mathematical convenience. He expected someone to come along and restore continuity. That didn't happen. Instead, other physicists took his idea seriously. Einstein used it to explain the photoelectric effect while light can knock electrons out of metal, but only if the light's frequency is high enough. He proposed that light itself comes in discrete packets, which we now call photons. Bohr used it to explain the structure of the atom, why electrons orbit at specific distances and emit specific colors of light. He showed that the orbits are quantized. De Broglie extended it, suggesting that not just light, but matter itself has wave-like properties, and those properties are governed by Planck's constant. Heisenberg derived the uncertainty principle, showing that Planck's constant sets a fundamental limit on how much you can know about a system. Schrödinger wrote an equation that describes how quantum systems evolve. Planck's constant is in that equation. Every major development in quantum mechanics traces back to Planck's insight. Every single one. And all of it confirms the same thing. Energy is quantized. Action is quantized. Reality has a smaller scale. Planck's constant is not an artifact of our theories. It's a feature of the universe. It's one of the most important numbers in physics. Maybe the most important, because it tells you something that nothing else does. It tells you that the universe has a floor, a bottom, a point beyond which you cannot go, not because of technological limits, but because the universe itself stops making sense. And that floor is not arbitrary, it's precise. It's measurable. It's the same everywhere in the universe as far as we can tell. Planck's constant is a universal constant, like the speed of light, like the gravitational constant. But unlike those, it doesn't just describe a property of space or time or gravity. It describes the structure of reality itself. It's a constant that tells you the universe is quantum. And here's the final twist. Planck didn't discover this because he was looking for the structure of reality. He discovered it because he was trying to fix a graph. He wasn't a philosopher. He wasn't a visionary. He was a careful, methodical scientist who wanted to make the numbers match the data. And in doing so, he found something that no one expected. Something that changed everything. That's how science works sometimes. The biggest discoveries aren't planned. They're stumbled into. They're the result of someone paying close attention to a discrepancy, a mismatch, a place where the theory doesn't fit. Planck noticed that mismatch. And instead of ignoring it or dismissing it, he took it seriously. And what he found was the edge of the universe. Not the edge in space, the edge in scale. The point where reality stops being continuous and starts being discrete. The point where the universe reveals that it's not made of infinitely divisible stuff. It's made of quanta, little indivisible chunks of action. That's the discovery. That's what no one explains. The universe is not smooth. It never was. And the constant that proves it, the number that defines the scale of that discreteness, is named after a man who spent years wishing it wasn't true. But it is true. And once you see it, you can't unsee it. You start to realize that everything you think of as continuous motion, energy, time, change is actually made of steps. Tiny, invisible steps. So small you'll never notice them in daily life, but always there. The universe flickers. It jumps. It operates in discrete increments. And Planck's constant is the size of those increments. That's reality. Not the reality we imagine. Not the reality that feels intuitive. But the reality that is. And there's nothing beneath it.